Good morning, everyone, and welcome to the first FOSSR webinar dedicated to the presentation of the FOSSR Policy Learning Platform, one of the services that will be made available by the FOSSR research infrastructure. I'm Claudia Pennacchiotti from the IRPPS CNR, which is the institute in charge of the webinar organization. This webinar is part of a series of online seminar planned as part of the FOSSR research infrastructure financed by PNRR funds. And the webinar format is aimed at giving visibility and enhanced services and tools made available by the FOSSR research infrastructure. Last year, 3 online webinars are already conducted, presenting some of the FOSSR services and tools, and namely the first one focused on the Italian online probability panel, the second one focused on a specific tool for agent-based modeling, and the third one focused on the FOSSR Open Cloud. You can find more information on the webinar realized on the Zenodo cloud space of the FOSSR project. Going back to this first webinar, will be presented a tutorial of the Policy Learning Platform, which is a FOSSR tool for learning optimal policies from data. A tutorial will be illustrated, and the main functionalities and the value for the researcher, policymakers, and stakeholders involved in the decision-making process will be presented. Over the next 2 hours, our speakers, Giovanni Cerulli, Federico Brogi, and Fabrizio Fausti, and 2 discussants, Barbara Guardabascio and the Professor Marco Ventura, will discuss and present this tool. Let me introduce our speakers and discussants. Giovanni Cerulli is the scientific coordinator of the FOSSR project and the coordinator of the research group which developed the policy learning platform, and is a researcher at the Ircres CNR Institute. Federico Brogi and Fabrizio Fausti are researchers at the Istat. Federico is a researcher in statistics, and Fabrizio is a physicist. Professor Barbara Guardabascio is Associate Professor at the Department of Economics at the University of Perugia, and Marco Ventura is Associate Professor of Econometrics at the Department of Economic and Law at the University, La Sapienza. Let me finally thank the FOSSR Communication Group, Alessandra, Serena, Rita, and Alexia, for their great work that makes this event and the other FOSSR event possible with their support. And notice that the seminar is being recorded. So now enjoy the webinar, and I give the floor to Giovanni.
Thank you very much. Can you hear me? Yes? Or
yes, very
yes,
well.
Yes, we can.
Thank you. I just want to thank Claudia for the organization of the web seminar, and also Alessandra, Rita, and Serena for the organization, and all the speakers that also, and the discussant that accepted to provide us with some very useful insights, I imagine, about what we are going to do. Okay, the FOSSR Policy Learning Platform is part of the task 5.1 in the FOSSR project, Fostering Open Science and Social Science Research, which is a PNRR project in Italy, 32 million euros for developing the the first open science cloud for social research in Italy, the first and the largest, I would say, and a series of tools, data, and facilities for carrying out research in the social science, in the socioeconomic science. Just a few words about the aim of the project: building the Italian Open Science Cloud for the social sciences, focusing on many very, very hot economic and societal challenges, including demography and societal aspects like aging, wealth distribution, inequalities, migration, social behaviors, with models for agent-based models and social simulations, as well as experimental economics, structure of the economy, with a study of innovative firms and structural change in terms of economic structural change, and public policies. And I would say that this seminar is very focused on some facility for public policies. And the main idea is that of design for the future policy that, based on what happened in the past, are able to increase the welfare and the impact in particular for the future. Okay, within these the FOSSR, we can find the PLP, the Policy Learning Platform. To be honest, today we're going to be a little more, technical than in other webinars. In particular, what I want to say is that we will provide you with 3 platforms that are able to deal with the policy learning platform. A platform in Stata, one in R, and one in Python. But this is not the policy learning platform, no one of these, because the policy learning platform will be, at the very end of the project, will be a web application, something that the policymaker or the user can access and can use using Windows without any knowledge of Stata, any knowledge of R, any knowledge of Python. So it will be completely a graphical interface, user interface device. Okay, however, today we're going to, for more advanced users, we're going to show how to implement the PLP in the 3 different platforms, software platforms. And of course, I would say that in a few lines of code, you will be able to run very, very substantial stuff. Okay, so that's what is my point here. I will be very fast, but because I want to leave my colleagues time for explaining in detail other things, and I don't want to take too much time for this, but I would say that the policy learning platform is in a middle ground, or if you want, is an intersection between 2 big topics in statistics and econometrics and artificial intelligence, which is machine learning on the one hand for prediction, and we see that prediction is extremely important here, and causal inference for counterfactual decisions, because whatever decision is based on counterfactuals. So this gives rise to data-driven decision making or optimal policy learning. Sometimes we speak about data-driven decision making as a more general box within which the optimal policy learning is one part of the content. Okay, let me go ahead. What is optimal policy learning? In a few words, in a nutshell, we would say that that policy learning is a way to automate optimal decisions whenever we are dealing with policies in terms of policies that needs to be in an ex ante way be carried out yet. Let me explain this. We have some very past policies that have been already run. We want to learn the optimal decision policy from these data sets that is basically representing what happened in the past, and we want to project in the future the possible treatment assignments, as I'll try to explain, that maximize the impact of the welfare. And this is based on predictions, and the prediction entails the central role of a machine learning as well as causal inference. So in a very, very simplified way, I might say that policy learning is a process of increasing welfare time by time by reiterating policies over time. And which kind of policies and in what sense we are speaking of optimality? What we want to optimize is the treatment assignment. You know that the treatment assignment identifies the rule that we use for identifying the beneficiaries of the policy. So we have a population that eligible people, and we would like to select only those that possibly are more able to increase their welfare by their action and the impact of the policy for the entire society. So this is a pure social planning in a very modern way. But we will do this, we will fine-tune the treatment assignment using different possible policy classes, because in the social sciences and in everyday behaviors, we may have a different kind of decision rules that we can use. For example, threshold-based, for example, linear combination policies or decision trees policies that are more sequential than the previous ones. We will focus on the three. We do not have time to spend too much time on explaining the difference between them, but the main idea is that we can address exactly this by the software we have created. And of course, we have to summarize the welfare. And sometimes we speak about maximizing the welfare, sometimes about the impact. Impact and welfare are two different things, but the same policy rules that maximize the welfare maximizes the impact and vice versa. So in this case, in our application and our implementation, we will focus mainly on maximizing the impact, so the effect of the policy, but it's the same. Okay, what is the problem? We have a policymaker with objectives and constraints, for example, legal constraints or budgetary constraints, and he has to take decisions. And the main decisions we are looking at are selecting the right individuals to pick up. And in this sense, the selection process is at the core of what is going on. So you see the red apple that represents exactly the guy that we want effectively pick up in the system. I want to also show you that in a few words that the policy learning process is part of the more general policy cycle decision-making process. And you see that we start from eligibility, and we follow different steps in terms of self-selection and the selection of the individual to that will participate in the policy, and then we have the development of the policy, the process of the policy, the unit behavior, the ex post evaluation, which is the past, and based on the ex post evaluation, we are able to learn in an ex post way and to predict the future effects that have an effect on the way in which the selection is made and the itinerary project evaluation is made. In other words, my point is that we need this kind of learning because it is very central for our understanding of what's going on. And I thank Rita for providing this wonderful graphical infographic for this scheme. Well, again, conceptually, this is a very, a very straightforward way to represent what the policy learning platform does. We are looking for an optimal location of treatment, right? But we have some budgetary constraints. We have also other eligibility constraints, and we have just to locate, to provide an individual with a binary treatment variable, treated or untreated. So it's the assignment rule that we have to discover, the optimal assigning rule. And you see that we start from the characteristics of the individual. We evaluate the treatment effect that we have over these individuals, and we consider a new population, and we take a decisions of the new population about which one is going to be treated and which one not. So this is basically the scheme. Okay, this scheme can be represented by a flow that is more understandable. This is the real functioning of the system, okay? Okay, suppose that you are a policymaker and you have your own data about the past policy, and your own data is made of a triplet. This triplet is made of course, the 8 individuals that you have considered in your past policy. 4 out of 8 have been treated, and you see also the characteristics of them. And the Y is the variable of welfare variable that we are considering. For example, this might be income, for example, okay? So we have treated and untreated, their characteristics. Of course, in the reality, we have many of them, not just one X, but many X's. And one outcome variable, which represent the individual utility value, okay, or whatever you want to call it. Well, by the make CATI, what is the make CATI? The make CATI is just a program that is going to transform this data set into a single value for each individual, a single number. This number represents the individual treatment effect, the effect of the single individual given the characteristics of him. So Mr. I with characteristics I will get this value, which is a number. This may be 10, 11, whatever is a number. For example, for myself, for Gio, this may be 10. And this is exactly the value of the treatment effect. The idiosyncratic means the individual treatment effect for Gio, for myself, thanks to machine learning and causal inference. So it's not that easy to get it. We need some theory and some procedure to get it. But finally, the meaning is that one. It's just the individual effect. Then, given this is given from the past policy, right? So what we have to do now is to generate a prediction over a new population. This new population is called by X prime. But before doing that, we have to decide which kind of policy do we want to run in the new situation, in the new prospective policies. And the policymaker may decide whether he wants to run a threshold base, a linear combination, or a decision tree policy. Having decided that, he can use the OPL command, and we will see that by grid search, so it's a totally data-driven, will come up with this fundamental output. What is the final output of the platform? Very simple. It's just a T star, which is the new allocation over the new population. Mr. 9, Mr. 10, and Mr. 11 weren't here, right? Of course, possibly you may have someone even in the past policy and in the new policy, but just for you to clarify that, to have it very clear, I put it different individuals here. So what we know about them, what we know is in green. What is in green, the numbers in greens is what is known. And the values in red is the output of the policy learning platform. So what is the main output of the policy learning platform? It's very simple. It's a vector, if you want, a series of ones and zeros for each individual that identifies whether this individual should be or shouldn't be treated, shouldn't be a beneficiary or should be a beneficiary. For example, Mr. 9 should be picked up, should be a beneficiary. But Mr. 11, no, Mr. 11 should not receive the policy. Why? Because it is optimal for the society as a whole to provide treatment to Mr. 9, but no treatment to Mr. 11. It's not that we are unjust, we are just. We are just because this is the best situation for the society. And finally, we come up with a single number here, which is a scalar, a number, a single number, and this single number, that means 1,000, let's say, it's just either welfare or impact. Depends on where we are working with. In our platform, we use the impact, but we can also estimate the welfare. This is something that we're going to do, but that's not important because there is a one-to-one relationship between the impact that we get and the welfare that we get. But anyway, we are maximizing the welfare as well. A few words about policy classes. policy classes in terms of what we do is just characterized by decision boundaries. In other words, they are different rules that we are going to use for selecting individuals. The classical one that we use in everyday life, this is not an invention of Gio or of Federico or Fabrizio. This is what we do in everyday life. In everyday life, we take decisions by threshold. For example, I have, just to give you an example, when you have to decide whether a student should pass or shouldn't pass the exam, you have a threshold for the oral exam, a threshold for the written exam, and you decide whether the individual will pass the exam if he scores better than C2 and more than C1. Or linear combination is the same. For example, you can put different weights to the marks. For example, X1 may be the mark for the oral exam, and X2 is the mark for the written exam. And so we have just to decide the C1, C2, and C3 that maximize the welfare. And same for the fixed decision 3. Here we have to define not the 3, in this case, 2 parameters. In this case, 3 parameters, C1, C2, C3. Here we have to define 6 parameters. In other words, T1, T2, T3, but also which variable we are going to select in the first node, and which one in the second, and which one in the third. Okay, so we use this. This is a simple example of a constraint impact maximization. In a univariate case, it means that we only consider one variable for selecting individuals, because the selection variables, of course, have to be decided beforehand, like in this case. And you see that, for example, in this case, it's optimal to treat all individuals with an age larger than 42 years. So if, for example, in deciding this policy, you will consider people, for example, on the left, or you choose another kind of threshold, for example, 30 or 35, you will run suboptimally. It is optimal just to run the policy using a threshold for deciding who is going to be treated, age equal to 42. And this is the maximum average, the maximum impact of welfare achievable. Okay, this final trade-off, and this is what it's possible also to generate a menu of different possible allocations depending on the taste of the policymaker. The policymaker can prefer to be here, can prefer to be here, and can prefer to be here. What is the difference? The difference is that many times we may have different trade-offs. For example, sometimes the optimal allocation implies that only one individual should be treated. Well, this is not very nice. We would like more people to be treated. So we can prefer this allocation, or this allocation in which we see that many individuals are treated, like in the case of the orange dots. What is the difference between these different allocations? Is the welfare. If you want sometimes to treat more people, the level of the welfare reduces. And so you are not running at the optimal level. But the optimal level is unfeasible, because the optimal level requires just to treat one guy. So maybe the policymaker can prefer to be here, to be here, to be here, even if the cost may be a lower level of welfare. He prefers to treat more people. Okay, I finished, because now the software implementation is in Stata, in R in Python. Now I'm going to show you what I did in Stata. And then Federico is going to show you the R implementation, and the Python implementation will be provided by Fabrizio de Fausti. Well, let me say that the 3 commands are really, really, really similar, but not exactly the same, in that some has a few things more and a few things less. And there are some differences that, however, the big bulk of what is going to be done is the same. And then there are some peculiarities that are a little different. And we will show this along this presentation. Okay, now I'm going to show you, for my part, the optimal policy learning. And this is the package that I carried out in Stata, and now it has been accepted in the Stata journal, and it will be published in the journal very soon. Okay, thank you very much for this presentation. Now for this, sorry for this for being there, and then I want to show you the implementation in Stata. Okay, suppose that you are a Stata user. So you know quite well about Stata, but you do not need to be a Stata programmer. No, you just need to be a Stata user, which is different. So you just need to know how to upload data sets and basically do some housekeeping with the data, and then basically run commands. So the commands we are using here is the OPL, that you can access the documentation by OPL, help OPL. So I click here, and you see that you come up with the documentation, which is a Stata package for optimal policy learning. And this is made of these commands. These commands are all important. In particular, the make cate is the one we use for estimating the conditional average treatment effect. So in other words, the idiosyncratic effect in the past policy, as well as the projection in the new policy. So we have two different cate that we get. The first is the training cate, which is the effect in the older policy, and the other one is the effect in the future policy that, of course, is just projected, just predicted. And then, according to whether you want to run a threshold-based policy, a linear combination policy, or a decision tree policy, you can use one of these different commands. Okay, for example, click on the cate, and you can access the of course the make cate function or command documentation, and you see that this takes as inputs the outcome, which is, for example, income, let's say, the features, the characteristics of the individual, that are the variables that you have in your data set, the treatment variable, and then here we put the name for the new cate, cate, and the name for the training cate. It's not really important, that one, because the name can be whatever, Ciccio, Mario, Luigi, whatever you want, okay? It's not a problem with this name. This will be automatically generated, these two variables, with the name you decide to give them. But then, more importantly, you have to provide the new data. The new data is the population X prime, is the new population, or the data about the new population, the X's, basically, of the new population that will receive potentially the treatment. We don't know who is going to be treated. This has to be decided by the model. But we introduce the entire population here. And then we have to decide which model and which algorithm we want to run. Okay, if we look at the model, we have a different model for estimating the conditional average treatment effect. I don't have time to get into the theory, but the most popular is the T-learner. The T-learner is what is just called in the literature regression adjustment approach, and estimating the tau, the idiosyncratic effect, by prediction from two different regressions. I don't go into the details now. But what is important is that it can accommodate the different form of the output. For example, if the output is continuous, we can use a linear model. If the output is a numerical, is a binary, we can use the logit. If it's countable Poisson, if it is F logit, this is fractional. And then we can decide the type of algorithm to run, and we can run the RA, the regression adjustment, as I said, or we can use a doubly robust approach, which is the CF-AIPW of Robert Kennedy, that been developed recently. I also had some exchange with him, and I implemented this method as well. Anyway, and then what we have finally is a series of returns. And the most important returns is basically the old cate sorry, the old CADI, so the one of the old policy and the one of the new policy, and then we can use this for estimating the effect. Okay, going back, I want to show you exactly how to estimate the optimal threshold in a threshold-based optimal policy learning. I will not cover the other ones. Linear combination and decision tree will be covered by Federico and Fabrizio, but I will speak just of the threshold-based one. Okay. In order to find the optimal one, I click here on this documentation. This is the threshold-based optimal policy learning one. So how I have to do? Remember that from the previous command, CADI, make CADI, we got the CADI, okay? And this variable has been generated by the make CADI. And using the make CADI, we can introduce this variable inside here in the CADI option. Then we decide the two variables as a selection variables that we want to use. For example, in some cases, this might be, for example, age and education. So in this case, we only can consider two selection variables. I forgot to say that this is the only limitation so far of this model, that this model supports only two selection variables, but this is quite reasonable in applications because our policymakers generally do not use more than two policy variables in order to decide who is going to be treated. And so, and then what is the main output? Are the C1 and C2. Remember in the slides, so I come back to the slides now if you want. So the idea is that we want to identify C1 and C2, which are optimal in this case for describing the optimal rule that we want to run. So going back here, these are C1 best and C2 best, okay? And then we can find this. Okay, application. Okay, this example run the entire application, starts with a data set, which is the data set is, let me just show you the data set with a describe. The data set is a data set about a training policy for basically active labor market policies. In other words, we have many unemployed people and we want to give them, we provide them with a training and to see after 2 years whether they will be employed or not, or whether is the level of the income after 2 years from the policy. The policy is a training, so let individual to have a training. Okay, we have the train is the variable of interest for us because it is a 0-1 variable. Then we have many different control variables, as you can see, and the outcome variable generally is unemployment in 78 or real earnings in 78. In this example, I will consider real earnings in 78. So the main idea is that we want to learn the policy, the optimal policy from this data set. The data set, let me show you, is very, you see, training age of individuals. This is Mr. 1, Mr. 2, Mr. 3, Mr. 4. For example, this guy is treated, the age is 27, the education is 11 years of education, he's a black guy, is not married, and blah, blah, blah. Okay, so typical socioeconomic data set. So I have the data set. Now I have to generate the old and the new policy. Of course, I don't have the new population. I generate this from the old population. So it's like a sort of just a simplifying example. In the reality, you will have the training data set, which is the old policy, which is one data set, and another data set, which is the new population data set. Here, I just generate a split of the initial data to generate the two data sets separately. So the 60% now is the data set over which we learn the policy, and 40% is the new population over which we are going to predict the optimal policy. Okay, I use this new data set, the JTrain, which is the same, but of course, if we count the number of units, we see that now it's 267 instead of 480, of course. Then I consider the real earning in 78 as my outcome. As my covariates or confounders, I use this one, real learning 74, 75, age square and no degree. This is the training variable. And these are, very important, these are the two variables used for as a selection variables, age and months of training, okay, into Z. Okay, I have all the ingredients now to run the make CADE and generate the CADE in the training data set and the CADE in the testing data set. In other words, in the new population, okay? And as you can see, I will call it, the new CADE will be called my CADE new. This is the name that I put inside. You can put whatever you want. And for the training CADE, I put my CADE train, and you can put whatever other kind of name. What is important is the new data. The new data is a JTrain test. This is a data set that is in your directory. So in your directory, we have already generated this. You may have this as a separate file because it's part of the new population that you have over which you want to run the policy in the future. Okay, the type of model is a regression adjustment. The model is a linear model because the regression adjustment can take different models, but my Y is continuous. And so I use a linear model in this case. If my Y was, let's say, binary, for example, employed and not employed, I might have been using, for example, the logit approach, the logit model, sorry. Okay, so I run this, and if I run this, I get the result. This is a result on the average treatment effect or whatever in the past policy. That's not important for us. But anyway, we have also this information. Then we are going to select into T the CADE for the new policy. Okay, then we only consider the command is going to generate the training. Let me show you the training. This is just a flag indicating that this is a training unit. In other words, this is someone belonging to the old policy, and this is someone, for example, Mr. 269 is a new guy that is in the new population that over which we are potentially running the policy. Okay, so I just coming back. I just consider I keep only the new individuals because now I'm focusing on the new policy. Okay, I drop this. It is not important, and now I run my command by using exactly the new CADE, the CADE that I get from make CADE only for the news and we using as selection variable these two variables, age and months of training. So I click here, and this is what I get. Okay, this is the main result. The main result is just these two numbers, C1 and C2, which are optimal. As you can see, we have several different optima. We're going to take the average, which is a 0.6 and 0.8. This is the optimal one. Can you switch off the mic? Sorry. Okay. So this is what we get. Now we have to run the model and see what's happened when we use exactly this optimal threshold. How can we do that? We have to go back, or if you want, we can go here. And now we can use another command, which is optimal TBC. C indicates that now we are going to calculate the optimal allocation, the optimal treated and untreated individual using a specific vector of C. In this case, we have only C1 and C2. So the command is very similar to the previous one. So we have again we have the two selection variables, the new CADE, the C1 and C2 that now have to be inserted, and then we have the graphical representation with the name of the variable that we want to consider as dependent variable. This is not important. This is just for graphical representation. It's not something that affects the estimates. Okay, I go down, I redo this now. Look, I open up the data set, get the train test again, just for generating the old and the new population. I consider the older population over which I already ran the policy. So I just redo the model and calculate the make CADE again. So we have exactly, I did the same as we did before. So I do the same here. I do the same here. Same here. Same here. Remember, OPLTB is going to generate the two values here and here. So we are fine with this. And now I put them into two boxes. Global is a boxes in Stata. So in other words, I record these into two boxes. And then I'm going to consider this this command in which I, as a C1 and C2, I consider the optimal C1 and the optimal C2 provided by the previous commands. And also I ask for a graph. So I click here, and this is the results. Okay, the results is analytical. I mean, you have a table of results, which is this one. Okay, which kind of policy have you run? A threshold-based. Main result. Which kind of learner? The learner was the regression adjustment. Okay. Number of units is this one. Target variable real earning is 78. Threshold value for C1 is 0.6 and 0.8. We know that they are optimal because we got this before. And the average unconstrained welfare is 2. And the average constrained welfare is even larger in this case, 2.8, which is quite good. This is the maximum one that we can get in this case. How many treated do we get? Oh, just 1%. Only 2 people, which is very, very bad, right? But just for you to give an idea of it. And then we, having that, we have the e-return list, and we have all the information about the results that you have seen before, now located here. So you can generate the tables or whatever. You can also take this and generate a table from this. For example, you can take these and put them into ChatGPT, and ChatGPT will provide you with a wonderful table to be published, even in LaTeX or whatever. You do not need any effort for this. And then, okay, the final thing is, but all this information are well represented in this graph that is going to show exactly who is going to be treated, who is not to be treated. So only 2 individuals are optimal to be treated. And you see that this is the level of the welfare that we reached. Constraint means that we use the policy learning, the threshold-based policy. And then also what you can see is that the percentage is just 1% of the treated. So what is my suggestion here, as I try to explain in the slides, and I go to the slides again, what we have to do is to move a little around the optimal value and see whether there are options that provide us with a larger number of treated, a larger number of individuals to treat, and finally to select one of them that are more feasible, because this one is not feasible. With just 2 people to treat is not a policy that can be run. But if we are going to explore around the maximum value, maybe we can find an allocation which is more feasible, more reasonable, and we can use it. It's up to you. It's up to you, policymaker. It's up to you, analyst, what you want to do. You are very free to do this. And in order to do this, how can you do this? By going back into this, using this command. And instead of using C1 at the optimal level, you're going to play with them. For example, instead of putting here 0.6, you can put 0.4, here 0.3, and see what's going on. And so just by modifying you can have you can have different things. Just for you to know whether it's possible to, I'm going to show you just in 1 second. For example, if I put here 0.3 and here, for example, 0.4, okay, well, it's much better now, all right? So what we have is that these ones. Of course, this guy can be there, but they will not be treated. Why? Because they have a tau which is negative. And so in this case, they should not be treated. So not only people to be in the right-hand side in this quadrant is just a sufficient, not a necessary condition to be treated. So in other words, what is important is to look at the colors. Finally, where can we find the treated and untreated? You go. What is generated is this variable that you can tab. This variable is just to provide us with the frequencies 161 are untreated, and 17 must be or should be treated. And of course, you can find this variable at the very end here. And this is the variable deciding exactly this is the optimal policy. The optimal policy is 1001. And observe that is different from the policy that were run. Sorry, no, not here. It's not here. Okay, forget it. Anyway, this is what the main output. And now you know who is going to be treated and who is not going to be treated. Finished. That's all. Very simple, very straightforward. And I mean, of course, you may have other possible situations, but mainly this is what's going on. Okay, I finished, and I leave the floor to Federico for the R implementation. All right.
Thank you, Giovanni. Let me share
yes,
my
I'm
screen.
going just to eliminate my screen. Yes, you can go ahead. Yeah.
Can you see my presentation?
Yes.
Yes.
Okay. Hi, everyone. Thank you for participating in this webinar. I'm going to introduce you to the R version of the OPL, and I'm very glad to announce today that the OPLR package is available on the CRAN, the official R page. You can get the package going to this link, or just going to the CRAN page, where you can find some documentation, the reference manual, and the package source here. Okay. Or you can go, if you are already an R user, you already know how to get the package. Going to the RStudio and using the toolbar, going from Tools, Istat Package, and searching for the OPL package written with the capital letters. After that, you can install the package or record the library from the console. Okay, after presenting the package, we will go to RStudio to run together a live tutorial to analyze a practical example. Whether you are an expert in causal inference or new to this concept, I hope this session will provide you with valuable tools for your analysis. So let's get started with the OPLR package. This R package includes more or less the same function of the Stata version, make cut for the estimation of the conditional average treatment effect, the three different policy learning approaches. We are going to see together an application on the linear combination one, and we added the overlapping function to compare the policy data set. The make cut function is designed to estimate the conditional average treatment effect in a binary policy setting. For model fitting and prediction, the users can choose between the general linear models or the random forest. And the average treatment estimation is given by a regression adjustment model. This is the very first version of the package, and more models will be implemented soon. To run make cut, we had to take some steps. But first of all, we need to give the input data set. As already explained by Giovanni, we need two data sets. An old policy related on the old policy that has been already carried out, and another one related to the new policy. Here in this example, we are going to call it train and test data, paraphrasing the machine learning language, because we have just one original data set that we are going to split into into two different data sets regarding the old and the new policy. Other input parameters are the model type that we are going to implement, and the typical evaluation statistical setting stuff, just like the Y variable, the outcome variable, the treatment variable, which is binary 0, 1, that we are going to call W, and the covariates selected by the user. To run the regression adjustment model, we perform the calculation of the average treatment effect in 2 steps. The first one is regarding the old policy. So we take the trained data set and we split it into 2 groups using the W treatment variable. The 2 groups are related to the treated and untreated. After that, the function will run, will fit separate models for both groups on the trained data set, and the prediction will be generated on the same groups and the same data set. So we will get the average treatment effect on the old policy, just calculating the average difference in the predicted outcomes between the 2 groups. The model fitting and predicting the prediction can be generated with a GLM or a random forest model chosen by the user. The second step is regarding the new policy. Here is where we learn from the past. So we take the models trained over the old policy data set, and we use these models to calculate the average treatment effect on the new policy. So the predictions are generated for both groups treated and untreated on the new dataset, the test dataset, the dataset regarding the new policy. And the average treatment effect calculated over the new policy will be the average difference in the predicted outcomes between treated and untreated in this dataset. After that, these predictive values will be added to the dataset, so to run the following OPL functions. The OPL functions will be implemented only over the new policy dataset. This function provide more outputs, more estimation, like the difference in mean estimation or average treatment effect on the treated only for the treated group or untreated group. The function that we added is for the R package is the overlapping function. This function is designed to compare the distribution between the 2 data sets, the train and the test data set, regarding the old and the new policy. The function will perform a principal component analysis on a set of covariates selected by the user for both train and test set. The PCA reduces the dimensionality of the data and while retaining the most important information. So we will take the first principal component extracted for both data set, and over these values we will perform the function will perform a Kolmogorov-Smirnov test to check if the distribution of the train and the test set are significantly different or not. And after that, the overlap function will generate a density plot over the first principal component of both data sets to help a visual to permit a visual comparison of the 2 distribution, just to have more information to intuitively assess the overlap between the 2 functions. After that, after checking the overlap of the distribution, we can perform the OPL, the optimal learning function. In this case, we are going to use the linear combination approach. This function, I think, can be of the great help while implementing policy, for example, in some income support program where the allocation is based on 2 variables, and we want to use as an assignment rule a weighted sum of the standardized variable of these 2 variables. For example, in an income support program, we can use the household income and the number of children as to assign the treatment. In the R version, we use just one function to the optimal allocation and for the scenario analysis. This function allows two options. If the user does not provide the threshold values, the function will calculate the optimal allocation. Otherwise, if the user will give the C values, the input as an input, we can calculate and evaluate different allocations. This function needs some input parameters. The first one is the output data frame from the make_cate function, which is called make_cate result. After that, we need to select the selection variables for thresholding and policy assignment. The other input needed is the W treatment variable. And so, as we already explained, C1, C2, and C3 are now optional values depending on which kind of option we want to perform. The function will perform the standardization of the selection variables in a range from 0 to 1, and after that, the function will determine the treatment assignment using, first of all, only the cate estimated in the make_cate function, which are positive. And if the C1, C2, and C3 values are not provided by the user, a grid search will be performed over all the possible threshold values to maximize the average constraint welfare. Sorry. So the final step of the function is to assign the treatment using the linear combination function, and the output generated includes the average constraint welfare, the unconstrained welfare, the optimal threshold if our user input or not, and a summary of the treatment assignment with the number or percentage of treated and untreated units. A scatter plot will help the visualization of these results. So now let's move to R for a practical demonstration. Okay. So this is some line of codes to have an example, practical example of this, how to use this this function. Okay, if you're not our user, this is how to get the package running code, or you can click here on Tools and Install Package and search for OPL and click here Install to get the package. Okay, we are going to run this example on a different data set, which is the 1991 Survey of Income and Program Participation, which is a longitudinal data set collected by the US Census Bureau. And this data set provides detailed information on economic and demographic characteristics of individuals and households in the United States. The data set is already uploaded. We can have a brief look where we can find a brief look to the variables and labels. So our Y variables, our outcome variable will be net TFA, which is the net total financial asset owned by the household, and net because it's subtracting debts. For example, we have some, and E401 is the treatment variable, which is a binary variable, indicating if this the individual participated or not into a type of employer-sponsored retirement saving plan, which is called 401. The other variables will be used as covariates. For example, if the household is owned or not. We have the family size, the age, level of education, here years of education of the head of the household, and so on. So to run this example, we have to split the original data set into train and test, representing the old and the new policy. We are going to split with a sample, okay, with the sample function. And after that, we have to create the statistical setting. We have to give these names to the data set variable. So we have to record the data set variable net TFA as the Y variable. So here we have to run the controls and the treatment dummy variable and the selected variable as Z, okay? So this is the statistical setting that we have to run. After that, before running the make-cate function, we have to choose the model for fitting and prediction. The first example will be with using the generalized linear models with the family Gaussian, which is just the representing the linear model. Here I put some more information because we can implement the Poisson for non-negative discrete counts and so on. Now we are ready to perform the make-cate to calculate the average treatment effect. The function needs some input, the model, the train data, the test data, and the variable from the statistical setting. We need to store the result in a new data set called the make-cate result, which will be the input data set for the OPL function. So just running this line of code, we can obtain the result, the estimation result for the old policy data set and the new policy data set. So we can see that the almost 10,000 observation in the original data set is being split into an old policy data set with almost 6,000 observation, and the numbers of observation for the new policies of almost 4,000. Here we have a summary of which estimator is used, the outcome model, and the calculation, the result of the ATE prediction is our CATE, the result of the main result of make-cate for the old policy and for the new policy. Well, here we can compare the two results and check and immediately check that the new policy is giving a higher level of treatment effect. If we want, we can, I just want to show you briefly that it's very easy to change the model and the learning and to apply a different model on the make-cate function, just specifying the new model, random forest, and the two options needed for the model. N3, number of tree, which is the number of trees in the forest, and M-try, which is the number of randomly selected predictor, a predictor at each split node. Okay, so just running these new values, we can check the result for the random forest. Here I'm not going to assign the result to make-cate result because I want to go on with the previous result. Okay, and here we have the prediction for the new model, the regression adjustment and the outcome model. Okay, let's go on fast because time is running. Okay, so the overlapping function is, we can run the overlapping function and very easily obtain the result of the Kolmogorov-Smirnov test and the graph, the density graph, to compare the train and the test set. As we can see, the values, the p-value, the test statistic value, and the p-value are telling us that we cannot reject the null hypothesis. So there is no significant difference between the two data sets. And we can go on to predict, to find the optimal allocation with the OPL function. Before running the OPL, we just need to select only the new policy data. Okay. So the OPL LCC it can be run specifying or not specifying the threshold values and storing the result in the OPL LC result, which is a new data set with the that can store all the result for each unit. The linear combination, optimal linear combination, is run very easily, and here we obtain all the summary results: the policy class, the number of units, the optimal linear combination parameters, the average unconstrained welfare, the average constrained welfare, which is higher than the unconstrained welfare, because we are maximize the impact of our policy, the percentage of treated units, which is very low because it's 0.5 percentage. In fact, we have only 20 treated over 400 units. Okay, on the left here we have the graph. We can open up and check that here we have the decision boundary and the unit, the treated units on the upper part of the graph. To check different allocation, we can specify the C values, the threshold values. Specified by the user, C1 0.5, C2 0.4, and C3 0.7, just to change a little what happened optimizing the threshold. So the result is that we have a higher number of treated units, and which is now the 5%, and we can easily check the difference in the constrained welfare, increasing the number of treated units.
There is a reduction. There is a reduction in the welfare, right?
Yes, the reduction in welfare and increase the number of treated units, and the reduction in the welfare generated. Okay, as the time is running, I leave the floor to Fabrizio. Thank you for your long attention.
Thank you, Federico. I share my screen. Hello, everyone. Thanks Federico, thanks Giovanni, thanks organizer of this seminar. I think this project is very interesting and important. In these few minutes, in my speech, I will show the implementation of the optimal policy learning in Python language. Previously, Giovanni and Federico have shown OPL implemented in various programming languages as Stata and R. Then we ask why we need to develop OPL in another programming language and why Python. In this slide, in this graph, I show you how Python is the most popular programming language for data science on two important platforms used by software developers, GitHub and Stack Overflow. And why Python is so popular? Python is very powerful, has very powerful library, as Panda or scikit-learn for data processing, data manipulation, and machine learning algorithms. Other libraries, as PyTorch or TensorFlow, are the main choice for artificial intelligence application. Python has a large community of developers who share code, which allows to find a solution for any area. And it has a consolidated library for communicating with database and web application, which make it interoperable. Python is also highly scalable. These features make it Python the preferred language for the implementation of policy learning platform of the FOSSR project. Okay, now I present the library for OPL developed in Python. PyOPL is the name. In this demo, I show you directly how to implement a policy learning process with decision tree. So the first step is import the library. This is the command in Python, and this is the help, a very small help of the function available. The functions are the same that Federico showed in the previous talk. And in this process, the first step is load the dataset to train and test the predictive model for the treatment effect. So this is the command that's used for load a data frame for train and test. And here I define the target variable, control variable, treatment variables, and constraint variables. The dataset of this demo is the same presented previously by Federico. Next step is create an instance of the class OPL by the constructor of the class. And now the next step is run the make_ate function. In the optimal policy learning, as previously mentioned, is based on the construction of two models aimed at predicting the effect of the policy both when the policy is applied and when is not applied to the unit. Therefore, building an accurate predictive model and evaluating its quality are very fundamental requirements of the process. In the OPL developed in Python, to train predictor models, it is possible to choose from a set of machine learning algorithms, selecting the one most suitable for specific domain, such as linear regression, random forest, lasso, and so on. The process of model selection of the model can be performed by measuring the mean absolute percent error in an out-of-sample approach using a k-fold validation technique and a grid search process to optimize the choice of the hyperparameters of the algorithm. The choice, this choice ensures the best possible model and provide a measure of its quality. This is the learner implemented in the Python OPL, linear regression, lasso, random forest, histogram-based gradient boosting, and extreme gradient boosting. Now I show you how to run Mecate. The command is similar of Stata and R. The arguments are the X-train and X-test, the list of target and the other variables, constraint and control variables. This Boolean, if you want select the model by out of sample approach, and this is the learner name. In this case, I show you the learner lasso. Now I run the code. This is the output of the lasso learner for the treated model and not treated model. We can see that the output of specific output of lasso is the algorithm feature analysis. So you can see which predictor are very important for the prediction. You can see the grid search used to select the best model and the best hyperparameter selected by the grid search process. And we use a k-fold validation with 5 folds. This is the output, the scatter plot of the predicted and the target variable and the predicted target variable, and this is the mean absolute percent error for the non-treated model and for the treated model. So we have trained the two models with the other output for the coefficient of lasso. This is the number of treated, of not treated, and the average treatment effect for the train and for the test. Now I show you Mecate with another learner, XGBoost. I run the code. Is the same of the previous shell, but change just the name of the learner, XGBoost. This is the output. We have a better performance of the error of the model. We have a mean absolute percent error of 4% for the not treated and 5% for the treated. And this is the train average treatment effect, and this is for the test. And the output of this function is a table. This table is make cut result. I show you the table. Here there is a column make cut that have the conditional average treatment effect, and the column of instance of the train and the new instance for the policy. This is the function overlapping implemented. Okay, this is the output for the threshold based and for the linear combination, but it's the same show by Giovanni and Federico in the previous presentation. But now I show you the last optimal policy learning decision tree. That is a policy learning, is a decision tree that have just one level fixed level of decision tree. This is the selection of the unit in the threshold base and linear combination. This is the space in function of the constraint for the threshold base and function of the other parameter for linear combination. In this approach, this is the fixed decision tree. The search of the best configuration of the parameter have to find the best configuration for the constraints C1, C2, C3, and for the variable that compare in each node, that can be age or education. So we have 6 parameters to search for find the best configuration of the welfare in under constraint. This is the formula in semistic approach. The solution is the union of two logic condition from the left side of the tree and the right side of the tree. And in this scheme, I show you the powerful of the search of the treated in this configuration that can be more flexible than the threshold based and linear combination approach. So I show you how to run the OPL decision tree. I have to create a new table with the output of the make cut result, just with the new instance of the table. And I run this. So this is just the new instance. And I run the function with this table and the constraint z variable. In this moment, the algorithm searches the best configuration of 6 parameters. It's quite strange. Okay. Was strange. It was
because you're online. Because you're online.
Yes. Okay. Now this is the welfare constraint calculated in this approach. We have 4 solutions that give the same welfare constraint. So we want the unit. We can choose the unit relative of each configuration. So in this moment, the code asks me which configuration you want select. I want to select the configuration 0 with 0 index. This is the output of this configuration with this value of the constraint and variable. This is the enzymistic formula. You can see that this part of the formula does not solution because is intersection of disjunct set. And just this part is give the resolution with this unit that is the output of the function. We have the average constraint welfare, that is this, and the number of unit treated, 11, and this is the percentage of the treated. If I want select another index, I have no rerun this function. I can give another parameter in the OPL DT function. It choose that I can select another index, for example, 1. And this is the output without the calculation, slow calculation before of the configuration with index 1, that is this one. Okay, and this is the configuration. Okay, thank you. I finished. I give the floor, I don't know, maybe Giovanni.
Okay. No, I think Claudia.
Okay.
Yes. So thanks. The floor is for Marco Ventura. The next.
Okay. Thank you so much. Can you hear me?
Yes.
Yeah. I try to share the screen. Just a moment. Okay, you should see my screen now.
Yes.
Okay, so good afternoon, everybody, and thanks for this invitation. I wish to congratulate those who contributed most, or at least even for small contribution to the production of this very interesting policy tool. It is very, very interesting, and again, I congratulate everybody. So I think that it is, given its complexity, I think that it took a long time. So it would be a sort of curiosity for myself to know how many years to develop it. But apart from that, I think that it is very interesting from a scientific point of view to see that using OPL, it is possible to overcome a distinction that so far has been in the literature of policy evaluation, because OPL puts together ex post and ex ante evaluation. And while the scientific community and also the European Commission has been unanimous so far to considering the counterfactual approach as a unique tool for the ex post evaluation, I think that the same cannot be said for ex ante evaluation. And with OPL, it seems to me that it is possible somehow to apply the ex post the counterfactual ex post methodology to ex ante evaluation. This is quite an interesting scientific case. So making it easily available to the users for Python users, R users, or Stata user, or in the future, even by a Windows framework, that could be very, very, very useful. So for that, I congratulate to those who have started thinking of disseminating it. A second leverage point is that I think that it could make easier to communicate policy evaluation, because so far as a practitioner and working also with policymakers, I've seen that there is a very, very high and a huge difficulty in communicating the outcome from a counterfactual approach. Think of the simplest estimator in this field, the IV, which stands for Instrumental Variable Estimator. It's quite difficult to explain to a policymaker, to any policymaker, that the result that you get about the policy that has already been implemented holds true only for a subsample of individuals, and you don't know who, the late theorem. So it's a bit embarrassing to talk with policymakers, and I hope that this tool will bring together the two different parts, or the two different actors of this story, the policy evaluation. So my first question is strictly related to this observation, and I would like to know whether you have already had the possibility to work, or at least to present the OPL tool to any policymaker, and if you have an idea, if you have a feedback about their sentiment about OPL. Of course, this is the first question. And the second one is more is not so strictly technical, but it moves from the fact that, especially considering the welfare state, most of the policies are aimed at helping disadvantaged units, while by disadvantage we can consider, for instance, former drug addicted, or former inmates, or unemployed, or households, refugees, whatever. So in my experience, whenever the disadvantaged word come into play, it brings a lot of problems, a lot of consequences, because everything is endogenous. You don't know whether they are disadvantaged because of a certain feature, or whether if that specific feature comes from the fact that they are disadvantaged. So my issue is that being disadvantaged necessarily will generate a very low expected outcome, whatever you want to measure the outcome. So it seems to me that at this point of the work, the OPL will drive them out from the selection process. So we leave the disadvantage out of the future treatment sample. So in this case, if this is true, if this applies, the OPL will fail in selecting the right person. Well, where by right, I mean the most disadvantaged, characterized by a very low expected outcome. So I wonder whether it is possible to take into account somehow this specific feature, or if even better, if I'm missing something in this point, actually the current routine is still able to keep into account this specific characteristic. So yes, is it possible to take into account in the future this aspect? The third question, I've seen that the three softwares are not completely overlapped. So which one do you prefer? I don't know to who refer this question, because I think that each author will answer mine, of course, but in general. So which one do you think is more flexible, if any? Okay, so very short intervention and very precise question. So I would like to leave the floor back to Giovanni or any other who would like to answer. Thank you.
I think we can go on with Barbara, and then we can make
I didn't know if I should wait for answer or not.
Okay.
Okay.
If Giovanni and the others agree, we can collect all the questions and then go on with the answers.
Yes.
Giovanni, it's okay for you?
Yes, it is.
So can you see my screen?
Yes.
Okay, good. Okay, so I just come directly, skip the main results that you already present, that is here in my draft, for have an idea of what you do and for follow up your main results. And I do directly to my three main points. I do three different exercises. In the first part, I try to look at a possible example for each one of the three kind of methodology that you introduced, and so the three strategies, and I look for which kind of policy we can try to analyze with the three strategy you suggest. I move to some technical aspect and more general consideration. First of all, for the three different approaches, we saw the first, the threshold-based policy, and I try to imagine a first example that can be, for instance, have subsidies for business in crisis. So the possible scenario is a government that wants to award subsidies to companies that are affected by an economic crisis based on some criteria. And we need to have a selection of all the possible variables that can be made based on financial indicators such as liquidity or profitability. And in this case, the optimal threshold is nothing else than an algorithm that provides an optimal threshold in terms of return on equity and cash flow, below which a company can be considered eligible or not. Other example, assignment of scholarship to students with a certain family income or minimum academic score, or access to welfare program or poverty indicators based on what is named is below a certain threshold. The second possibility, the linear combination, what can be this example, professional retraining program. For instance, a government agency that want to select the candidates for a training program for unemployed. And in this case, we can look at factors such as years, age, educational level, and think about the linear combination of these elements in order to considering the eligibility or an individual to be included in the training program or not. And the algorithm can find the optimal combination of this factor that maximize their employment rate. Other possibilities are assignment of tax incentive or business based on combination of investment in research and development, or determining insular rate based on combination of age, accident, history, mile, so far so on. For what about the decision tree, I immediately think about screening programs. And for instance, imagine healthcare system that want to optimize identification of patient at risk for a chronic disease in order to decide what to who provide a vaccine or something like that. And the algorithm can build a decision tree using BMI, glucose level, age, familiarity, and so far so on, and construct a decision rule based on a tree. It is also possible to think about the assignment of loans based on credit history and income, or the identification of beneficiaries for assistance programs combining multiple vulnerability criteria. This is the parts in which I do a kind of effort for thinking about if I can immediately imagine a possible application of these different approaches that you suggested, and I clearly found a well-precise area of government strategy that can be applied or tested through your application. So this is the first effort that I do. On the other side, I go looking better at what can be the limitation due to the algorithm, and in reference to the make-kate, I look at the possibility of considering just a binary treatment, and I'm looking at the possibility of look also to handle continuous or multiple level treatment. Moreover, I see that it relies on regression adjustment for causal inference, and in this case, we have no assumption about unmeasured confounding. And moreover, I think about the possibility of improved data collection by reducing bias in policy evaluation. For what about the limitation in terms of the OPL, I see that the three algorithms help policymakers to assign policies based on different approaches, we say. But we have a lack of complexity in the threshold-based policies. Indeed, they may fail to capture more complex relations that can appear in the data. Moreover, the strong dependence that there is with respect to the make-kate can rely the results and the accuracy of the results on the prior kate estimation. So it means that there is a possible error in the estimation of the kate. We can have some problems and affect the outcomes at the end of the process. For what about computation and scalability limit, the grid search for optimal threshold can be resource intensive, and so from this point of view, I see some limitation on the explorability and the time consuming that sometimes can should be considered when a policy should be decided. I see several more general aspects for expansion, integration in terms of improving accessibility and data integration. My idea is how far is the idea of having a full open access database for policy related data. So there is the possibility to create a network or a way of interoperability in order to have data set also not nominally, that give us the opportunity to test policy, improve data collection, let the quality of the evaluation be better and better. Indeed, while by one side we are in the right direction in develop user-friendly interface for policymaker and provide comprehensive documentation and training results, and we need to take care about the availability of data. I also think to the possibility of integrate all our information with the more the new technology that comes out from the artificial intelligence technique to as a possible solution to clarify decision making process. In terms of real-time policy adaptation, I look for the possibility of monitoring this tool in real time. So considering the possibility of using this tool continuously while more data come available, replicate the exercise more and more time in order to correct over time the effect of a policy, and I think that the policy is not fixed once for all, but can be dynamically improved day by day, so but time by time. Also, if you think to the regional structure of Italy, you can think that can be adapted, taking care also to the space and the different region, different future, and adapt the results to the different context. And incorporate also real-time feedback that can come directly from the policy refinement. From an ethical and social consideration, I look for integrate fairness and equity measure in policy optimization, and I'm asking if it's possible by your side to ensure some compliance with the ethical guideline and privacy laws in this respect, and promote inclusivity in policy design and implementation. So this is, I'm asking if there is, you take care about the problem connected with ethical and social consideration to be addressed while you are using this data and making this consideration. And finally, I look for the possibility of expanding cross-disciplinary collaboration in terms of partnership between economists, data scientists, and policymakers to encourage knowledge sharing and through workshop and conference, and develop cross-institutional initiatives to enhance OPL applications. And that's it.
And thank you very much, Barbara and Marco. So I give the floor to the speakers to give an answer to Marco's questions on the OPL methodology and the sentiment of the policymakers, the issues of the selection mechanism, and which is the software do you prefer to develop OLP, and the point collected by Barbara. So she evidenced the possible application and limitation, the possible application of the OLP, but there are also some limitations linked to the CATE, the OLP, for example, the lack of complexity, scalability, limits, and so on. But she evidenced also the potentialities and the strength of the OLP, and she put some ethical and social constraints. She evidenced some possible ethical and social constraints. So I think now I give the floor to Giovanni and the other speakers. Yes.
Maybe I can start just responding to some of them, and maybe Federico and Fabrizio can respond to the others. So just a couple of them, maybe the one I'm going to pick up now. The first point, I want to reply to Marco about the role of disadvantaged people, the example of disadvantaged people, because I think this is very, very problematic whenever we have automated the decision makers. And you know that this is one of the problems that we also have in any machine learning based approach, in which there might be a reinforcement mechanisms that is going to be very, I mean, I would say, I mean, not racist, but very, very focused on just considering a few groups, and by excluding people that are weaker in the society, for example, like not to give jobs or treatment to black people, for example, just to give an idea, just because the past was made in that way. Okay, I have a reply to this. This is a very general, okay? This is not a problem of just a discriminatory, yes, this is the word, discriminatory actions based on these automated decision makers. There is a very huge debate in machine learning about that. My impression is that discriminatory data sets depends on past policies and past decisions. And if we are going to learn from the past, and in the past we had this kind of mechanisms that were, strictly speaking, very based on information that are, I mean, old, I would say, this problem can be very important. How can we deal with this in this specific case? Imagine that one of the selection variables might be the level of poverty of a person. And you might see that it's very convenient not to give, for example, the incentive to poor people. And it's better to give money to less poor people. Well, I have a question for you, and this is the point that maybe, okay, when an individual is poor, there's a big question. I mean, for example, the model can come up with a threshold with, ethically speaking, might be too low or too small. So I think that even if this is the maximum outcome that the society can get, maybe some further equity elements can be put into the model. And this is what we do with the menu approach. Have you seen the menu approach when we have different thresholds? So the main idea, you can renounce to some efficiency, which means you can lose some welfare effect in order to increase the number of treated, which means that in order to increase the number of poor that benefit from the treatment. We can do that. Of course, we cannot put everyone inside. Even among the poor, if you have a budgetary constraint, you have to decide to give money to the poor that have more possibility to do well in the future. You may say, but this is unjust. No, this is not unjust. This is the only thing that we can do with when we have a constraint in the money. If I had just 1 million of euros, and I have to decide which poor to treat, I would say, I'm obliged to decide that that one will be treated, that one will be treated, and that one will not be treated. It's exactly the same problem of vaccines. As you remember, we would like not to give vaccines to anyone, but someone is going to get the vaccine and going to die. We know that. We know that someone getting the vaccines are going to die. We know that. But the benefits and the costs are well balanced whenever you are going to run it in an optimal way. Because otherwise you might have many, many people dying because of this disease. The logic is similar, not exactly the same, but it's similar. So at a point, you cannot save the entire world. You have to decide because you are budgetary constrained. That's the only point. But you can decide to what extent you can reduce the welfare, which means reduce the efficiency in order to enlarge the number of people getting access to some, or if you want to be universalistic, like there is not decisions. Everyone is going to be taken. There is no decision. If you want to offer, for example, to people some medical assistance, and you say, I want to be universalistic to everyone to give medical assistance, there is no decision. There is no, this is just one decision, everyone. Because the ethical aspects is much more important than the efficiency part of the story. But that's something that we can do in certain contexts. But in other contexts, it's impossible because we do not have enough money for doing that. I do not speak about just the case of health. I'm just speaking of decision under budgetary constraints.
Yes, it
That's my
seems
point.
clear. It seems clear your point. Thank you very much, Giovanni. Thank you very much. Unfortunately, I must leave the floor. I must drop out. I really apologize, but unfortunately, it's a bit late for me. So thank you again. Thank you again for your invitation. It is a very interesting issue and topic and tool. Congratulations.
Thank you, Marco. Okay, I leave some other aspect to the other ones. I don't know if Federico or Fabrizio, if you want to reply to Barbara or to now.
I try to reply to the question about explainable EI. I think is a very important point because for a decision maker is a crucial point. Know why someone can be participate to a policy or not. So I think is a very important point. In the Python implementation, also in random forest in R, there is some simply approach to the implementation of the model, because for example, random forest, you can see the importance of the variable of the model. So you can see the mechanism about the variable more important of the model. So I think is an important thing. Also in another algorithm, such of course linear regression is interpretable, and also lasso that is implemented in Python offer lasso offer the possibility to see which variable predictor are more important for the prediction. So the point is very important, and we can explore another method to have the interpretability of the model, more complex method, but now we have just this solution. Thanks.
And I would like to, first of all, thank Marco, even if he had gone away, because the point that one of the major points of the policy learning platform is to reduce the gap, to reduce the distance between the policymaker and the research environment, because the policy learning platform want to bridge this gap. Just and to answer to Barbara, the policy learning platform users, we need to train the users to help them use the platform and to take all the benefits from this web application in terms of possibility to make complex calculation with an easy application, with a user-friendly application, and to interpret the results in the easiest way as possible. So the AI help may be very useful to make a step forward to clarify the use of these results. And I think that first about the data set availability and about the the possibility to reduce the bias for the policy treatment estimation. I think that FOSSR is going that way, because a very important effort is made on the data set, open source data set. I think that Giovanni can give some more detail about that. And I think that the example given by Barbara about the practical example on which we can perform this function, these packages, open the way to more users, more policies, and to give a help for the society with evidence-based results to better policies, to create better policies. About the language which is preferable, I don't know. Everyone, I think, is a Python user or R user or Stata user, and it depends on the power of each software, the possibility to run a code or another, open source or not. So I think that that's the reason why we implemented all this possibility, because I think that everyone wants to work in his own environment.
Yeah.
Thank you.
Thank you. Claudia, can I add just one thing before
yes, of
closing?
Course. Please, yes.
I just want to speak about FOSSR, the project.
Yes.
And just to say that this is a service, the LPL, the Policy Learning Platform is one of the tools of the many tools of FOSSR, of course, is maybe the most centered on policy evaluation, I would say. The second thing is that although we implemented this in 3 softwares, there will be, as I said at the beginning, there will be a web platform that do not need any knowledge of Stata, Python, or R, because it will be completely Windows driven. So in other words, will be just it will be an app, right? An app. So you can use this app for doing that. The third thing, just to reply also to what Federico said and what Barbara said about improving policy over time. The FOSSR is going to generate 2 very important surveys, original surveys of FOSSR, not only the traditional surveys that already are there, but 2 new ones that are the online research policy, online research probability dataset, and the internet online probability survey. So I would say these 2 surveys will have a great role, that of generating high frequency social, economic and social data, because we will have many different waves, even 4 or 5 over the years. This means that if we have within the questionnaires of these 2 important surveys questions about policies, we might monitor the policy change over, let's say, 1 year. Whatever policy, of course, whatever policy is, of course, time variant or over the years or whatever. But the very message is we are running exactly in that direction. If we have 3 important elements, data, computational ability, software, and theory for doing that. So I think that data is in what ORP and IOP are going to provide. Facilities in terms of computation and storage is what our data centers in FOSSR are going to do, and applications and theory like PLP, but not only that one. We have Pulpo, we have many others, but one like PLP that may be able to leverage these 2 components, data and computation, to provide very upfront methods for policy evaluation and societal improving attitude towards certain specific very hot policy challenges and social challenges like immigration or whatever kind of policy we can consider. I think there is a great advance. Of course, we have to be humble because, I think that we want to do a lot, but we also know about the limitation of everything. But we are very happy that we are going on in this direction. And of course, I thank also all the people in FOSSR, in the 9 work package of FOSSR that are every day working on this very important task of increasing our ability, let me say, to serve society by science. This is what we are doing, serving society by science. And I think it's a great endeavor and something that we should be, everyone of us in FOSS should be proud of, to be honest. Thank you very much to Claudia and to everyone organizing this.
So thank you, Giovanni, for these great words and for organizing and realizing this seminar with us. And thank you also to Federico, Fabrizio, Barbara and Marco for their great contributions. Thank you for staying with us this afternoon, and stay tuned on our social networks to have updates on our next events and dissemination events and seminars and training opportunities. So goodbye, everyone, and see you soon. Bye.
Thank you.
Bye.
Thank you very much, everyone, for the organization. Bye-bye. Thank you.
Bye.
Bye bye.